If T is a linear transformation from a vector space to itself, then of course we can apply T to any vector at all in the vector space. But sometimes we can find special vectors in the vector space where something special happens when we apply T. So let's look at that. So let's let T from V to itself be a linear transformation. Now if there is a vector little v in V and a scalar, let's say lambda, in the reals, such that T of V happens to be equal to lambda times V, then we call V an eigenvector of T with eigenvalue lambda. So for example, let's let P2 be polynomials of degree less than or equal to 2. And let's define T from P2 to itself by sending a polynomial to the derivative of x times the polynomial. So a0 plus a1x plus a2x squared gets mapped to derivative of a0x plus a1x squared plus a2x cubed, which is a0 plus 2a1x plus 3a2x squared. All right, now I'm going to show you what the eigenvectors and eigenvalues are of this map. And then in another video I'll tell you how to find them. But for now I'm just going to show you what they are and demonstrate that they're eigenvalues and eigenvectors. So, how to find eigenvectors and eigenvalues will be in another video. So for now I'm just going to tell you what they are. I claim that 1, x, and x squared are eigenvectors. With eigenvalues 1, 2, and 3, respectively. So, to prove this, I'll just apply the linear transformation to 1, to x, and x squared, and we'll see that each one gets mapped to a multiple of itself. So T of 1 equals the derivative of x times 1, which is derivative of x, which is 1. So 1 got mapped to 1 times itself. T of x is derivative of x times x, which is the derivative of x squared, which is 2x. So x got mapped to 2 times itself. t of x squared is derivative of x times x squared, which is derivative of x cubed, which is 3x squared. So x squared got mapped to 3 times itself. So each eigenvector gets mapped to a multiple of itself. And actually, eigen is the German word for self, or close to that. My German is actually not very good, but eigen is German for self or something very similar. All right, so there's some natural questions. One, how do we find eigenvectors and eigenvalues? And I'll show you in another video. Another question is, why are eigenvectors and eigenvalues interesting? So why do we bother including them in this course? And the answer is, if V has a basis B, little v1 through little vn, of eigenvectors, so if we can find a basis where all the basis elements are eigenvectors, with eigenvalues, let's say lambda 1 through lambda n, then the matrix of T with respect to the basis B is just the diagonal matrix with the eigenvalues on the diagonal. And diagonal matrices are nice for several reasons. One, multiplying by a diagonal matrix is easy. Sorry for the glare here. This is lambda 1 through lambda n on diagonal, and zeros everywhere else. So this makes multiplication easy. So if we have lambda 1 diagonal to lambda n, zeros everywhere else, times a vector, let's say a1 through an, then we get lambda 1a1, lambda 2a2, etc., up to lambda n an. So all we're doing is multiplying all the components of this vector by the eigenvalues. Raising to a power is easy too. So if we have lambda 1 through lambda n on the diagonal and zeros everywhere else, we raise that to the kth power, we just get lambda 1 to the k, lambda 2 to the k, etc., down to lambda n to the k. Still a diagonal matrix. All we did was raise the diagonal entries to the kth power. So the reason that this matrix is so nice So the reason that the matrix of T is diagonal is that column J equals the coordinate vector of T of Vj, where Vj comes from the basis. Now, since T of Vj equals lambda j Vj, so to say that the basis is eigenvectors with eigenvalues lambda 1 through lambda n means that T of V1 equals lambda 1 of V1, T of V2 is lambda 2 V2, etc. T of Vn is lambda n Vn. We have that T of Vj equals lambda j Vj, and then the coordinate vector of this with respect to the basis B is just, so lambda j Vj is 0 times V1 plus 0 times V2, etc. Lambda j times Vj, and then 0 times everyone else. So it's just a bunch of zeros, a lambda j, and then a bunch of zeros. So if we do that for all the columns, then we get this diagonal matrix. Now in the example we did before, T of 1 is equal to 1, T of x is equal to 2x, and T of x squared equals to 3x squared. So the matrix is 1, 0, 0, 0, 2, 0, 0, 0, 3. That is the matrix with respect to the basis of eigenvectors, which are 1, x, and x squared. So 1 is 1 times 1 plus 0x plus 0x squared. 2x is 0, 1 plus 2x plus 0x squared, and 3x squared is 0 times 1 plus 0 times x plus 3x squared. So we get this nice form. So as I said, this is easy to multiply vectors by. So if we have this matrix and we want to apply it to a0 plus a1x plus a2x squared, we just get a0, 2a1, 3a2. Just multiply all the components by 1, 2, and 3, respectively. Also, if we wanted to raise this to a power, say square it, we just square the diagonal entries. 1 squared is 1, 2 squared is 4, 3 squared is 9. I guess I can write in the couple of zeros here. Now in the example, the natural basis 1x x squared happens to be a basis of eigenvectors. This doesn't usually happen. In fact, this usually does not happen. So basis of eigenvectors is usually different from the natural basis. To find it, and we'll talk about exactly how to find it. It says natural basis, period, space, to find it. To find it, which we'll do in another video, we use a procedure which starts with the matrix of T with respect to any basis you want. So pick a basis, say the natural basis, find the matrix of T with respect to the natural basis, and then from there we'll find the eigenvectors and the eigenvalues. The end.